All right, let's go ahead and get started here. My name is Nihar Shah. I'm a senior development lead at Microsoft, working on the Hyper-V team. My team is in charge of the platform management and extensibility, and that includes the WMI interfaces for the platform. I'm also a contributing member at the DMTF system virtualization, partitioning, and clustering team, which defines a lot of the standards that our object model is based upon. So just a brief agenda about what we're going to cover today. The first thing is just a really brief overview talking about some of the key concepts in Hyper-V that we're going to be touching on throughout the presentation. Then we'll talk a little bit about virtual machines, what that object model looks like, and how you manage them. We'll go over a couple of use cases throughout, how to create a virtual machine. Then we'll look at some virtual devices, how virtual devices are added and removed from a machine, how they're modeled in WMI. And then resource pools, which are actually used to tell you about what the resources on the system are, how they can be allocated to virtual machines, and what the restrictions for those allocations might be. Another use case talking about attaching a VHD to a virtual machine so you can actually run something useful in it. And then we'll touch on networking. Networking has several different aspects: networking in a virtual machine, networking in the parent partition, etc. And we'll go over a detailed use case there as well. So the goals of this talk are basically to give a detailed overview of the WMI object model and talk about some of the best practices. One of the things, as I've been talking to a lot of people who have been using our WMI APIs, one of the things that has come up over and over again is, well, it's a huge set of APIs, there are properties and associations and all this stuff all over the place. How am I supposed to actually use it in order to get better performance out of it, better scalability out of it, and really just what is the right way, so to speak. And also, hopefully through the use cases, we'll get a better understanding of how to perform some of the common tasks that you're going to want to do using Hyper-V. So, brief overview. As I mentioned, our WMI interfaces are based on standard defined by the DMTF. We use version 2.12e of that standard. Now, when you actually look at the virtualization namespace through WMI, you'll notice a number of classes that are actually defined there. Some of them will be prefixed with CIM underscore or SIM underscore, and others will be prefixed with MSVM underscore. The CIM underscore classes are the ones defined by the DMTF, and those we basically treat as abstract classes, so they're never actually implemented. The MSVM underscore classes are actually used for the concrete implementation. So those are the ones that will actually be used by you when calling our APIs directly. So another concept that we're actually going to talk about quite a bit as we go through these APIs is snapshots. Snapshots are essentially a point-in-time representation of the virtual machine. What that means is you've got a configuration that describes what does a virtual machine look like, how much memory does it have, or how many processors, and what hard drive, VHD drive is it using, etc. So that's all described in the configuration of the VM. There's also disk state and runtime state associated with that VM if it happened to be running at the time that the snapshot was taken. So once you've taken a point-in-time representation of this VM, what do you do with that snapshot? Well, the main thing you're going to want to do is, at some point in the future, you're going to want to apply that snapshot back to the VM. So the scenario runs something like, you're running along, you take a snapshot, you go install your private drivers or your other environment, whatever, and you end up messing up your virtual machine. Well, what do? You want to go back to a clean state before you went and messed everything up. That's what you basically do when you're applying a snapshot. So when you apply a snapshot, the snapshot itself is unaffected. The properties that are described in that virtual machine at the time the snapshot was taken are basically copied over into the current virtual machine. So if your current virtual machine happened to have 2 gigabytes of RAM, but at the time that you took the snapshot you had 1 gigabyte of RAM, once you apply it, your virtual machine now has 1 gigabyte of RAM left. And the disk and runtime state from the time of that snapshot are also copied over. Another important point is that snapshots are actually read-only for the most part. There are 2 properties on a snapshot that you can actually modify, the name and the notes associated with it. Other than that, in order to kind of preserve the point-in-time representation of that snapshot, the rest of the properties, all the device state, etc., all of that is read-only. So let's talk about virtual machines and the object model surrounding that. Here's kind of a big verbose picture. Before we go on into the specifics here, a couple of things just about the diagrams that you'll see throughout this model. You'll see actually that I've got all these boxes and a bunch of lines connecting them. The boxes basically are representing actual concrete classes that are implemented by our model, and the lines represent association classes. Association classes basically are used to describe a relationship between various between various objects in the virtual machine model. So here we've got, for instance, at the top you'll see a line with element setting data on it. What that means is that there's an association class of type element setting data, and it is associating the computer system on the left with the virtual system setting data object way over on the right side. So it's just describing a relationship there that says these settings are within the context of this virtual machine. So the computer system object here represents the virtual machine itself. It's the central class off of which everything else kind of hangs. It'll describe things like, what is the state of my virtual machine? How long has it been running? Those sorts of things. Next, we have the virtual system setting data objects. So these describe the top level settings for your virtual machine. Now, you can see that there are actually 2 different instances of it here in this diagram, and that's to describe the current versus the snapshot settings for that VM. So the one in the middle there, or on the left side actually, describes what are the settings under which this virtual machine is currently running. The one on the right, and there may be more than one on the right side there, depending on how many snapshots you've actually taken. But that describes essentially what were the settings at the time that I took the snapshot for that virtual machine. Now, the way that you tell the difference between them is through the associations. Again, these give you the context to tell you exactly how they're related to this particular VM. You'll see on the left there, the left one is associated with the computer system using the settings defined state association. That says this is the current settings for the VM. And the element setting data association on the top is used to describe the relationship between a VM or a computer system object with its snapshot settings. Finally, we've got this virtual system global setting data, which is, again, another top-level setting for the virtual machine. The difference between this and the virtual system setting data that we just talked about is that these values don't get overwritten when you're applying a snapshot to a VM. So the virtual system setting data that we just talked about, as you apply snapshots, all the properties described in that object will get copied over into the current virtual machine. The virtual system global setting data, you might have things like security settings for the VM, or its name, or its storage location, that sort of thing described in the virtual system global setting data, and those things won't change as you apply snapshots back and forth. Next, we have the logical device. Logical device objects describe essentially the virtual devices running inside of that virtual machine. You'll have one device instance that describes every single device inside of your virtual machine. You'll have one for memory, you'll have one for your IDE controller, etc. Another thing to understand about the logical device objects, and this is actually key when you're trying to program against them, is that these instances are only surfaced when the virtual machine is actually running. If it's not in a running state, for instance, if the virtual machine is saved or it's powered off, these logical device instances don't actually exist on the system. Next, we have the resource allocation setting data instances over here. These describe the settings for each of your logical devices. So again, we've got current settings on the left and snapshot settings over on the right. And you'll have a one-to-one relationship between the current resource allocation setting data and a logical device when the virtual machine is running. So there's one to describe basically each of the devices that you have in your virtual machine. So MSVM underscore computer system. As I mentioned, the computer system class represents the virtual machine in the diagram we just looked at. However, it can also represent the physical machine. Now, the reason that we did this actually, it's goes back to the DMTF standard that we're based upon. And the reasoning was really, let's try to make these things look as if they were kind of physical machines and abstract away some of the virtualization aspects of it. That way, kind of going into the future, if you can just envision a world where nobody really cares whether that happens to be a virtual machine, a physical machine, etc. They just want to be able to view the machine and figure out, hey, what are the devices on this thing? How is it running right now? What are its characteristics? Without having to worry about whether it's virtual. Now, this does end up giving you a little bit of confusion because if you go and just enumerate all the computer system objects, you'll end up getting one that represents the physical machine and a whole bunch that represent all your virtual machines. And the way that you tell them apart is through this hosted dependency association. The hosted dependency association has two properties, the first of which is called antecedent, and that will always have a reference to the physical system, and the dependent will always be a reference to a virtual machine. So you'll essentially have as many instances of the hosted dependency association class as you have virtual machines on the system. And you can see the relationship on that diagram at the bottom. So some of the interesting things on the computer system class, especially when we're talking about the virtual machine instances of them, enabled state is a property on that class, which basically tells you what's the state of my VM. Is it running? Is it paused? Is it saved? Etc. It's also got some transitional states in there if it happens to be in the middle of one of those states. Request state change is the method that you actually use to enact a change on enabled state. So these are the 5 properties that you can set, or values that you can send into the request state change method. And finally, we've got this process ID. And again, this is just a sampling of some of the interesting properties. The process ID is interesting because if you open up Task Manager and actually try to track, all right, where is that virtual machine over there in Task Manager to see what its resource consumptions are or anything like that, well, you can't really tell the difference because they're all named vmwp.exe. And so this process ID will actually help you map a virtual machine to what you're seeing in Task Manager. So the virtual system setting data objects, we abbreviate this as VSSD just because it's a bit of a mouthful to talk about. These, as I said before, represent the current or the snapshot settings for the VM. And the way to tell them apart, the best practice way to tell them apart is via these associations that we talked about. Settings define state and element setting data. There's another way that you can actually tell them apart, which is a property called setting type. If you look at that property, there are 2 values that we use there. One is 3, which means this is the current setting, and another 5, which means this is a snapshot. Now, the reason that we don't recommend that you go down this route is it doesn't give you any context information. For instance, if you just enumerate all of the virtual system setting data objects whose setting type equals 5, you'll get every snapshot on the system, regardless of what virtual machine it happens to be associated with. It's not going to be terribly useful in most cases. So in order to get that context, again, follow the associations. again, some of the properties on the virtual system setting data that are interesting here. You've got the BIOS settings, NUMA settings. These are basically kind of the virtual system setting data at the end of the day is kind of a catch-all for the top-level settings that don't really fit anywhere else. So we don't have an actual NUMA device that spans processors and memory and etc. So that kind of gets stuck here. Same thing with BIOS. There's no BIOS device. So you get some of that catch-all behavior with the virtual system setting data object. Other things you have are the notes, which is just free-form string that you can associate with the virtual machine, which also becomes very interesting with snapshots, where you can actually say, all right, here's some notes. I have installed my OS and a couple of apps, and you can put that in the notes just so you can remind yourself what this snapshot meant. And this parent property is also interesting in the case of snapshots, which will basically allow you to understand what the relationship is between all your various snapshots. If you take a couple snapshots, and then you apply one back here, and you start running again, and you apply another one back there, you'll end up getting this big tree of snapshots, essentially. And to understand what that hierarchy looks like and what those relationships look like gets a little bit difficult. And the parent property basically allows you to reconstruct that tree. Next, we've got the virtual system global setting data, which we talked about. This is the object that has properties that don't get overwritten as you play with snapshots and apply them or delete them from the virtual machine. These have things like element name. Element name is actually used throughout our model. You'll see it all over the place. And this is basically where we store the friendly name, so to speak, of any object. This is different from, say, something like instance ID or some other GUIDs that you might see all over the place, where it doesn't have to be unique, but it's generally something that you might want to put into a user interface or something that the user would be able to understand. There are also things like, what should the automatic startup, shutdown, and recovery actions for this virtual machine be? If I happen to be shutting down my parent partition, what should the VM do? Should it also shut down? Should it save its state, etc.? Scope of residence is a property that we actually use for the security settings on that VM. It contains the ASMAN or the role-based scope for that virtual machine. And then you've got these data routes, the external and snapshot data routes, which essentially tell you where that the configuration and the data for that virtual machine is stored. So on to virtual machine management. There's one central class for managing virtual machines. It's called Virtual System Management Service. And it's basically, it doesn't have a whole lot of properties there that are interesting at all. It's basically all the methods that are really interesting. You can create virtual machines, delete them. You can add devices, delete devices, modify devices from the VM. You can take snapshots, apply snapshots, etc. This is the central place to actually perform actions on all your virtual machines. And then you've got this concept of embedded instance. So for those of you that are actually familiar with WMI in some other uses, you might be familiar with this put and delete concept. So you get an object, you make a couple of changes, and then you put that object back, and that's how you enact a change. Well, based on the DMTF model that we inherit from, you don't actually put any objects or delete them directly. Instead, you go through these methods on the virtual system management service to actually do all of that. And so we use this thing called embedded instances. So you call into a method, and one of the input parameters will be an embedded instance of, let's say, the virtual system setting data that we just talked about. Embedded instance basically just means it's a big formatted string that describes the class and a bunch of properties of that class instance. So when you send it into a method, it'll have a couple of key properties that uniquely identify the class, as well as what it is that you wanted to change or reference in some way. And they're fairly simple to put together, especially if you're using a .NET or PowerShell sort of a language. They have built-in APIs to actually take an object and serialize it into this embedded instance. So one other thing that's used throughout our model is this, what's called a concrete job object. So most of our methods actually do support asynchronous operations, which means you'll call into the method, it'll do some basic parameter checking. If there's an error there, it'll return an error directly. If there's not, then it'll actually kick off the job and immediately return to you. And it'll return 0 if it's succeeded synchronously, and it'll return 4096 if the operation was started and it's now running asynchronously. It'll also, one of the other out parameters of each of these methods will be a sim concrete job object. And that can be used to further track the progress of the operation, figure out when it's completed. And it'll also, if an error actually ends up happening halfway through the operation, you can get some rich error information from that object. And as I said, any other error, return code indicates an error. Things like invalid parameter, insufficient memory, etc. These things that we can actually catch before the operation's been kicked off, just in the basic validation. So we come to our first use case, which is essentially how to create a virtual machine. For those of you that aren't familiar with PowerShell, all of the use cases that we're going to go through here are in PowerShell. However, we'll focus on specific parts of these things that should be fairly agnostic about PowerShell itself. So just focusing on kind of the blue highlighted lines of each of these sections. So first thing we need to do when we're creating a virtual machine, create an instance of this virtual system global setting data object. That describes the top level settings of the virtual machine. Next, we set a couple of properties on there, whatever we want to set on there. Here, all that I'm setting is the element name, which is the friendly name of the virtual machine. So we're calling it myVM. And then we serialize it into an embedded instance. Again, this is if you're using PowerShell or a .NET language, it's fairly simple. It's just a single method call to serialize it into an embedded instance. Now that we've got that, we need to go call a method to say, hey, create this virtual machine. Well, remember, all the methods are sitting on this virtual system management service object. So we go out and we get an instance of the virtual system management service object, and we call the defined virtual system API, passing in the embedded instance that we constructed earlier of the virtual system global setting data. And that's it. You've created your virtual machine. Now, once you've called that API, let's assume that you didn't have any other catastrophic parameter type errors. Most likely what you'll end up getting is a return code of 4096. That's going to tell you, all right, we're going to start creating the virtual machine now. Now, once you get that 4096 error code, you get return code, you get the concrete job object, and you check, is it still running? If the job state property of that object is 3 or 4, that basically means that it's still running, it hasn't completed yet, no errors, no nothing. So just go ahead and loop for a while. And you can use this %complete property to actually figure out how far has this operation gotten. Finally, once the job state is no longer 3 or 4, that means the job is complete, your operation is completed somehow. Either it's errored out or it's completed successfully. If the job state equals 7, and these are predefined values in the sim model, so sometimes they're a little inconsistent between one part of the model and another, but they're essentially very interoperable with a lot of the other implementations. So if it equals 7, that means success. The virtual machine was actually created. If it equals anything else, that means there was some sort of an error, and you can call this getError API in order to get rich error information about what went wrong. So now we come to virtual devices. As I mentioned before, virtual devices are represented by this logical device object, and they're only surfaced when the VM is powered on, which basically means running, paused, or some transitional state. That means things like saved or powered off, etc. You're not going to see these objects at all. The associations with the logical device, the first one, as you can see on the bottom there, is system device. System device basically associates it with a particular virtual machine, so you know what virtual machine that device is running in. And the second one is the settings-defined state, which associates the logical device with its current settings that describe how that logical device is configured in the VM. Finally, we've got this emulated versus synthetic concept. And as you go through the APIs and the different classes that are defined, you'll see some of them described as, I have a synthetic Ethernet adapter as opposed to an emulated Ethernet adapter. Now the difference between them, emulated is essentially a little bit more compatible with different operating systems, and especially some down-level operating systems, etc. However, you do sacrifice some performance in that case. Synthetic, on the other hand, requires that you're running a particular driver inside of your virtual machines, which we provide as part of the Hyper-V platform, but it has to be installed inside the virtual machine, and that will essentially accelerate and give you a lot more performance on that device. So, virtual device settings. Those are, RASD is basically the abbreviation we use for the resource allocation setting data class. And these are used to basically describe either the current or the snapshot settings for a device. Now, we saw with the virtual system setting data, or VSSD object before, that's associated with the VM via settings defined state for the current or element setting data for a snapshot. Well, unfortunately, the resource allocation setting data, there's no such distinction. They're both, on the left side, you'll see the current resource allocation setting data, and on the right side, you'll see a snapshot instance of a resource allocation setting data. And they're both associated with the VSSD via the same association class. So, again, everything's contextual. Everything requires that you use associations in order to figure out exactly what you're looking at. So you're going to go from the VM, follow one of the associations to the VSSD you want, whether it's a snapshot or the current, and from there go down to the RASD instances to figure out what the settings for my device are on that particular snapshot or the current settings. So resource allocation setting data, unlike the logical devices that we were talking about, they're always present in the VM. It doesn't matter whether the VM's on, off, running or not. And the type of device described by that particular instance of resource allocation setting data is described by these three properties. First one is the resource type. This is typically something relatively generic, like IDE controller or disk or Ethernet port. And then you've got resource subtype and other resource type. These further classify or differentiate that particular type of device. So we were talking about synthetic and emulated Ethernet ports, for instance. So the resource subtype might say, I'm a synthetic Ethernet port, or I'm an emulated Ethernet port. The other resource type is essentially used when nothing exists in the current enumeration for resource type to describe this type of device. So, for instance, there's no fiber channel controller described in the resource type enumeration. So in that case, resource type will be 1, which means other, and other resource type is just a free-form string that'll describe the exact type of device that the RASD actually indicates. A couple of other properties on the RASD, parent and address. These describe the connection from the device into the virtual machine. Let's talk about address first. So that's basically for the Ethernet port we were talking about, for instance. That would be the MAC address for that Ethernet port. For a disk drive, for instance, it might be what bus address on the controller am I actually connected to. The parent, this is essentially used in storage for the most part in order to actually describe the hierarchy of storage devices. So the way that we've actually modeled storage in Hyper-V is you've got a controller, a set of drives attached to that controller, and a set of disks attached to those drives. So the parent property here will actually describe what my connectivity is. If I'm a disk drive, where exactly, which controller am I actually attached to? Am I IDE or a SCSI controller, etc. And then we've got the physical machine connectivity. That uses the host resource and connection properties. So if you wanted to connect down to a VHD file, for instance, you would use the connection property for that. If you wanted to connect down instead to a physical volume on your parent partition, you would use the host resource property for that. So the real differentiation between the host resource and connection is that the host resource is used for physical devices that you want to surface up into the virtual machine, whereas connection is used more to connect to things like a file or maybe a VLAN ID or something along those lines, which is yes, it happens to be something on the physical machine that I'm connecting down to, but it's not really a physical device there. It's just one of its various resources. So next we have this concept of resource pools. Resource pools are used in order to describe which types of resources may be added or removed from a virtual machine. If it doesn't have a resource pool, you can't add it to a virtual machine. Now, on the top left here, you've got the resource pool object. It has exactly the same sort of resource type, resource subtype, and other resource type property that the RASD has. So that'll basically allow you to see exactly what type of device might be added or removed from that virtual machine. On the right side of this diagram, you've got 4 instances of resource allocation setting data. What these describe basically are the default, minimum, maximum, and increment values for each of the properties that you can have. So essentially, it's telling you what the range of values you can actually configure this virtual device for. So for instance, in the resource allocation setting data, we've got a property called virtual quantity, and that tells you how much of this resource is actually being assigned. So in the default RASD up at the top, let's say we're talking about memory, we might say the default is 1 gig. You can run a lot of virtual machines with 1 gig, so we'll call that the default. Now the maximum is going to depend on, well, how much memory do you actually have in your system? Let's say you've got a 4 gig physical system. The maximum value that you can actually configure there would be 4 gigs. The minimum would be 8 megs. 8 megs is the minimum that you can actually allocate to a virtual machine and still expect it to be able to run. And the increment, the virtual quantity property in that instance of the RASD would basically tell you, well, you're not allowed to have odd values, for instance. So the increment might be 2, which means you always have to increase or decrease your virtual quantity by an even quantity. So the way that you actually use this whole resource pool model, first is you get an instance of the resource pool that you're looking for. Again, that's by using the resource type, resource subtype, and other resource type properties. You navigate over past the allocation capabilities to this default RASD that we talked about. Go ahead and get yourself a local copy of that thing. And then you're going to modify some of the values there to the specifics of the device that you actually want to add to the VM. So let's say you got this default memory RASD and it says virtual quantity is 1 gig, but you decide, no, I really want 2 gigs in my VM. Well, you change that property locally, being careful to respect the ranges defined in the other RASD instances that we looked at. We then convert the RASD into an embedded instance. Again, most of our methods take embedded instances as input parameters. And then you call the add virtual system resources method on the virtual system management service class. and that'll essentially add that device to your virtual machine. So let's go through a use case real quick about how we can add storage to a virtual machine. Now there are two types of storage. First is pass-through. That involves two classes essentially. You've got a controller and you've got a disk drive. That disk drive is going to be directly connected down to a volume on your physical system. With a VHD, however, you actually have three classes. You've got the same sort of controller, the same sort of disk drive. However, you've also got a logical disk. Now, the logical disk represents kind of the media that you're attaching to this drive. There's a one-to-one relationship between a disk drive and a logical disk. And the logical disk actually points to the VHD file that you're getting into the VM. So in order to actually add a VHD or a pass-through drive to a VM, let's take IDE for instance. First thing you need to do is go get an instance of the controller that exists in the VM. So here we are. We're going to get an instance of MSVM computer system whose name is myVM. That'll go and retrieve an instance of the VM. We need to follow that over to the virtual system setting data object using the settings defined state association. This is going to give me the current instance of the settings for the VM. From there, we follow the virtual system setting data component association to find the IDE controller that's allocated in this VM. And so we're looking for an instance of resource allocation setting data where the resource type on the last line there is equal to 5. 5 means IDE controller. And whose address is equal to 0. Remember, we talked about the address, which is what is the connection into the virtual machine look like? At what address in the virtual machine is this device located? So an address of 0 for an IDE controller is basically going to tell you, well, this is the primary IDE controller in that virtual machine. So now we've got our hands on the primary IDE controller. Next thing we need to do is we need to add a disk drive and connect it to that IDE controller. Well, we use the resource pool model for that. So here we've got a statement that's looking for an instance of MSVM underscore resource pool, where the resource type equals 22. 22 means disk drive. And the resource subtype is equal to Microsoft synthetic disk drive. We're going to add a synthetic drive to this virtual machine. Next, we follow along to the allocation capabilities, which, if you remember the diagram we looked at before, that's just kind of a point where the 4 RASDs on the right side we're hanging off of. And we follow over to find the default RASD that describes a Microsoft synthetic disk drive. And so we follow the settings defined capabilities association, and this value role that you see on the second line from the bottom, that's basically going to be 0 to identify the default instance of the RASD. Next, we have to configure the disk drive and add it to the virtual machine. Now, there are 2 properties that we have to configure on this drive. One is the connection up into the virtual machine. That's going to be in the parent property, where we point it to the IDE controller that we just retrieved. And the second is, well, where on that IDE controller is it actually going to be located? Should it be an IDE controller has 2 different addresses? Should it be at address 0 or address 1? So we're going to set it to 0 here. That's essentially going to make it your boot disk on the IDE drive, or on the IDE controller. Next, as we went over before, we serialize this into an embedded instance. Actually, this particular method, the add virtual system resources, takes an array of RASDs. So you could, for instance, add 5 different devices all in one single call if you wanted to. And finally, we call the add virtual system resources method to actually add the device to the virtual machine, getting the result back, and then, of course, using the same concrete job sort of terminology that we looked at before. So attaching storage to a disk drive, With the pass-through storage, again, you use the host resource property. It happens to be an array. In Hyper-V, we only use the first element of that array. And so you would set the host resource property on this disk drive RASD to point to the storage volume on your physical system. With a virtual hard disk, it essentially is the same thing that we just did to add the disk drive to the VM. So we have to add a logical disk device. Well, we go find a resource pool. Its resource type is 21, which stands for storage extent, and its resource subtype is Microsoft Virtual Hard Disk. So that's how you find the right pool. From there, you navigate over to the default RASD, get yourself a local copy of it, configure whatever settings you need to on there. In this case, you set the parent to the disk drive RASD that you just added to the VM, and the connection property to the file system path of the VHD. Finally, you call add virtual system resources. So as you can see, the methodology for adding devices, regardless of what type of device it is typically very, very similar. And essentially, this is what you're going to end up with if you go through both of those use cases. So we've got two resource allocation setting data instances on the right side there towards the bottom. The top one is the settings for the disk drive that we added as we were going through the PowerShell code. And the bottom one is the settings for the logical disk, which is essentially pointing to our VHD. So now let's talk about networking a little bit. Networking, actually, this is a pretty busy slide up here, but networking basically has three different connection types, going kind of from right to left here. First, we've got something called an external connection. What that's going to do is connect a virtual switch on your system down to a physical network adapter on your physical system. Next, we've got an internal or parent connection. What this is going to, what an internal connection is basically a connection between your virtual switch up into your physical operating system, your host operating system. And finally, we've got a virtual machine connection. This is basically a connection between the switch and a virtual machine. So the way that the switch actually ends up inserting itself into the stack is you've got a NIC on the bottom, you've got a virtual switch in the middle, and that virtual switch will pipe up to various partitions. One might be your host partition, where in this case Windows Server 2008 is running, and other connections, you might have 10 other connections to 10 other child partitions where your virtual machines are running. So going over each of these objects here in detail, the first one we've got at the bottom is the virtual switch device itself. Next, connected to the virtual switch are these switch ports. The switch ports are basically the connection points for the virtual switch. And they're actually completely agnostic of what type, when we talk about external, internal, virtual machine, etc., they're agnostic as to what type of device happens to be connecting into it. They're just, plug points essentially on a virtual switch. Now, in the case of the external or physical connection, when you're connecting the switch down to a physical NIC, we've got this class called external Ethernet port. And that's what you're going to end up connecting down into the switch port. In the case of the internal connection, you've got an internal Ethernet port. These actually have to be created separately and then connected up to the virtual switch through that switch port again. And finally, you've got the virtual machine, and you may have multiples of these per switch. And on the top left, you've got the computer system that represents the VM itself. And just below that, an Ethernet port object, which represents the virtual NIC inside of that VM that's connecting to the virtual switch. So a use case for networking. We'll basically go through and set up a switch with all three of those connections. So first, we've got this thing called the Virtual Switch Management Service. essentially the same sort of concept that we had with the virtual system management service. It's got a bunch of methods on it for creating, deleting, and managing virtual switches. Once we've got an instance of that, we call this create switch method on it. We pass in a couple of variables here. The interesting ones are, the first one is a GUID, which uniquely identifies that virtual switch. The second one is the friendly name, or the element name of that switch. And the third one, that 1024 that you see over there, that actually is the number of MAC addresses that that virtual switch is allowed to learn. Now, the reason that we expose this GUID of the virtual switch and allow a user to actually configure that, as opposed to virtual machines where we generate it automatically, excuse me, is that when you start migrating machines or start importing and exporting machines on different hosts, well, that virtual machine actually is referencing down into a particular switch uniquely by its GUID. So if you actually wanted to preserve some level of compatibility there, we actually expose the GUID so you can create a switch with the same GUID on each of those various machines, and then you won't have the problem with migration of those machines back and forth. Now that we've got a switch created, let's create an internal switch port. We call the create switch port method on the virtual switch service. We pass in the switch that we just created, and we create the GUID for that switch port. Now, we happen to give it the friendly name of internal switch port, just so we can reference it back again and know what its purpose is supposed to be. But as I said before, the switch ports are agnostic as to what their purpose are. And therefore, these next two blocks create two more switch ports, which really only differ by, well, we created a new GUID for each of them just so we can uniquely identify them, and the friendly name that we happen to give to it. Now, we've got 3 switch ports on the switch. Now it's time to actually start binding that switch down to the external NIC. So first thing to do is find an unbound physical NIC. You might have several physical NICs here. This actually is going to enumerate them all and select the first one, whose class name is MSVM_external Ethernet port. And there will be one of those instances for every physical NIC on your system. Next, you call this setup switch API. Now, setup switch is actually an interesting API. We have very granular APIs for if you wanted to bind a particular NIC to your switch and then connect it up into your parent partition, etc. The problem that you end up getting into here is at some point you're going to lose network connectivity because you're taking the existing bindings and switching them over on the switch. So if you remember the picture we were looking at before, you've got the external bindings between the switch and the physical NIC, and you've got the internal bindings between the physical NIC, between the switch and the physical partition. Well, as soon as you connect the switch to the external NIC, the parent partition is going to lose all network connectivity because you haven't set up the internal NIC yet. So this setup switch API is basically a helper API to do everything atomically. So yes, you will still momentarily end up losing network connectivity, but you won't get into a situation where you'll actually be broken and unable to complete the second step. So in setup switch, you can actually see there are a lot of things that we end up passing in here. First, we pass in the external switch port, which we had created before. We pass in the internal switch port and a reference to the physical NIC itself, which we just got above. Next, we pass in a GUID. This GUID uniquely identifies the internal NIC, or the internal Ethernet port that we have to create in order to make the connection to the parent partition, as well as the friendly name for that internal Ethernet port. Finally, we need to connect a virtual machine to this switch. Now, this looks a lot like some of the stuff that we saw when we were adding storage to the virtual machine, right? You get an instance of the resource pool where the resource type equals 10, which means Ethernet adapter, and the resource subtype equals Microsoft emulated Ethernet port. So we're going to add an emulated Ethernet adapter to the VM this time. The rest of this basically is doing the same thing, walking over to the allocation capabilities, and from there to the default RASD instance for this emulated Ethernet adapter. Next, we configure the settings for the virtual NIC. We've got the default settings for this virtual NIC now. The only thing that we really need to set on there is the connection. Where is this thing going to connect? What switch port on what switch is it going to connect down to? And that's going to be this VM switch port that we had created earlier. Again, after that, it's pretty much the same thing that we had looked at before. Serialize that RASD into an embedded instance, pass it into the add virtual system resources method, and your NIC is now added and connected down to that switch. So following up from this talk, we didn't have any, we walked through a lot of code today. We didn't really have any demos in this session. If you're looking for some more information on Hyper-V, get to see some demos as well, and how to automate using Hyper-V. There's another session on Thursday from 12 to 1:15 on enabling test automation. We also have a hands-on lab area, which I'll be there as long as several other people from the Hyper-V team. So that'll give you a hands-on opportunity to actually program against these APIs as we talked about them. And finally, please fill out the online evaluations. And the recording will be available on MicrosoftPDC.com. Finally, thank you. So, questions and answers. If anybody has any questions, we've got microphones. Please pick up a mic before asking the question so it gets captured. I'm sorry, mic doesn't seem to be on. Is there a switch on there?
Does it work now?
There we go, yeah.
Does all this work from remote as well?
Yes, all of our APIs actually work either locally or remotely. And that's actually part of the problem when we were talking about the switch. Once if you don't use the setup switch API that we were talking about, you'll end up losing network connectivity if you're coming from a remote connection. And that's the reason why setup switch was actually added in the first place.
I know there's, if I look at cluster and WMI configuration, there is some problem with the security. Do you have any similar problems?
In what sense?
Okay, in the sense of when I want to configure the cluster machine with WMI from a remote machine, then creating the cluster and adding resources and so on, that really doesn't work.
Okay.
There's some problems.
So the security model that we use through WMI is actually based on ASMAN. It's a role-based security model. So we don't actually rely on the individual pieces, the individual files, for instance, or resources being properly ACLed, which is some of the problem that you find in some of the other security models. So with a role-based model, we can basically assign a single role, and operations to that role, and say, okay, you are now allowed to connect to this virtual machine, regardless of what resources it needs to use underneath, and then we'll use a local system account to actually, read and write from those resources. So, it's got its own challenges to work with, but essentially it is configurable. There's a separate set of COM interfaces in the ASMAN infrastructure, which we take advantage of. And then we've got our WMI interfaces in the virtualization realm, where you can actually set the scopes for all your various virtual machines or network resources, etc.
Okay, thank you.
Thank you.
I have two questions.
Yes.
you know the System Center virtual machine managers?
Yes.
You know the moving of the VHDs, is that all programmable through the WMI interface? Can you do all that through WMI?
Moving VHDs from where to where?
From machines, so from hosts, so you can actually migrate VHDs live while they're running.
Okay.
Or is this something
No, I just want to make sure that I'm understanding actually what you're saying. So in SCVMM, System Center Virtual Machine Manager, you're able to migrate virtual machines and their VHDs.
the VHDs, yeah, across from host to host and online.
Right. So that's actually a feature that it's not exposed directly through our WMI APIs. It is something that basically, in order to take advantage of that, you actually, SCVMM relies on clustering,
Yeah.
and a clustered file system for that.
Okay, so it is not WMI.
It is not through WMI.
And have you any WMI event providers that can actually give you indications of when you create VMs and you know, any of the devices? Is there any?
Yes, absolutely. We basically make use of the intrinsic and several extrinsic events that WMI uses just natively. So you've got the instance creation event, instance modification event, etc. And you can register for those, and you will get notifications for that. So there are, you know, it's kind of, from a client perspective, it really doesn't matter. But in terms of our implementation, about half of our objects just use the intrinsic events. The extrinsic events, for the sake of performance, have been implemented on some of the more commonly used objects. So,
can you also install the OS from the WMI onto that virtual machine? You install the components, but I didn't see you like install, create or install the OS and then run the OS.
No, essentially. The Hyper-V WMI APIs are essentially built for creating and managing the virtual machine at kind of the configuration, device, and disk level. Not so much what goes inside of the storage on the virtual machine. Kind of the approach that we've taken is for each virtual machine to be isolated from each other and from the host operating system in terms of what the contents inside of that are. So there's no mechanism for us to inject any data, such as you know, installing an operating system inside of your virtual machine.
What does that? Just the regular methods.
Yeah, you know, we've got, you know, Pixie Boot can be supported. You can use throw a CD in the drive and attach your virtual machine to that CD or DVD, and that'll install the operating system. It's essentially treated very much like a physical system would be at that point.
So I just want to qualify what the guy asked earlier. SCVMM lets you run PowerShell scripts to get it, right?
Yes.
So couldn't he run a PowerShell script to tell SCVMM to migrate a VM from one server host to another?
Absolutely. I'm sorry. Yeah.
So I just want to make sure he knows he could do it if he has SCVMM. It's just that's not a feature built into the native
into the
Hyper-V
platform.
APIs.
Yes. Yes. Thank you for that. And actually, one of the other points when I was talking about clustering as well is that you know, I was talking very specifically about the Hyper-V WMI APIs, not you know, clustering has its own WMI APIs through which you can actually achieve what that person was asking.
Yeah, my question's along the same. Is the SCVMM, what's the because that has a lot of really strong, really easy to use WMI namespaces in it already, which really builds on top of this. So what's the plan with both of those two paths? Because you have yours as the underlying foundation, but SCVMM, I just found them a lot easier to use than this. I mean, so what's the plan between the two paths?
Yeah. So, I mean, SCVMM has done a great job actually with abstracting a lot of the complicated parts of this model that we've been talking about. They've got PowerShell scripts and commandlets, etc. that they've actually used and built on top of our APIs. Now, as far as a plan for kind of synergy going forward, we're essentially following a standard, the DMTF standard that we're based upon. We're going to continue following that standard, and what that basically entails is making sure that things are defined in a very granular method. You can do everything that the platform allows you to do through our APIs, and sometimes that means that you have to make multiple calls or do a lot of fine-grained configuration like this. SCVMM obviously kind of abstracts all of that and says, we're going to make a couple of decisions for the user and expose other things to the user. And that's going to be kind of a similar paradigm going forward. That's part of what SCVMM's charter really is to make things easier, not just for managing Hyper-V, but SCVMM also manages other platforms such as VMware's platform, as well as Zen.
One's free for TLS. Right. SCVMM costs money and requires a domain. So
Yes, absolutely. Hyper-V is included with, or is actually a part of the Windows operating system, whereas SCVMM is a separate product, and that's, again, part of the value that they add in terms of management. Okay, thank you very much.